Neutrino scientists might spend their whole careers building beautiful and intricate machines to try to see neutrinos, and treasure every last one they find. But then some dark matter scientist accidentally snags a couple in their dark matter detector and is more disappointed than delighted. Why do dark matter physicists think that neutrinos are the worst? That's what we're talking about today on Even Bananas. There's a lot of evidence of some kind of unseen mass or dark matter filling the universe. There are many theories about what it actually is, but it's almost certainly nothing we know about, including neutrinos. You might remember we've discussed that before in this video. Nevertheless, our favourite ghostly particles can pose a problem for certain dark matter searchers, particularly WIMPs. These so-called weakly interacting massive particles are theoretical particles that have mass, typically quite a lot of mass by particle standards, and only interact weakly with nuclei. WIMP hunters are not that different from neutrino hunters. They wait for interactions in big, sensitive detectors that need protection from cosmic rays, so they tend to be built deep underground. Turns out, a mile of rock can stop a lot of noise. But can it stop a neutrino? Clearly, no, or else a lot of underground neutrino experiments would be off to a poor start. But that means that dark matter detectors are always going to have some neutrinos scooting through that might interact in the detector. The real problems start when you can't tell the difference between a WIMP and a sneaky neutrino that shows up uninvited. Speaking of sneakily showing up, though in this case very much invited, Dr. Kimberly Palladino is a WIMP hunter who works on the Lux Zeppelin experiment, which uses liquid xenon to search for dark matter. Maybe she can help us understand exactly why dark matter scientists think neutrinos are the worst. Hi, Kim.
Oh, Kirsty.
Now, surely you can tell the difference in your detectors between these massive dark matter particles and almost massless neutrinos.
Well, it's not the mass that directly affects what we see, but the momentum, which is the mass times the velocity. And in that case, if you have a very low mass neutrino moving at very high speeds and a high mass WIMP moving at a low speed, you might come out with about the same momentum.
So how would you ever know if you spotted dark matter or if it's just a rogue neutrino?
In some cases, it's easier to tell than in others. Some neutrinos rock up to a costume party dressed as dark matter, but you don't have to look very hard to realize it's not a dark matter particle. But other neutrinos have really great costumes, so it can be much harder to tell. So far, we've only seen a handful of neutrinos in bad costumes at our parties, but eventually they're going to get pretty crafty. This is what we call an exclusion plot, and we use it to show where we've searched for dark matter in terms of how heavy a particle would be versus how strongly it would interact. As you can see, we've ruled out heavy particles with fairly strong interactions with our current detectors. Essentially, if a dark matter particle had this mass and this interaction strength, we would have already seen it. As our experiments get more sensitive, we're able to search over more options, and this line gets lower and further across. But at the bottom here, our detectors pick up more and more neutrinos. Some of them, like these boron-8 neutrinos, which come from the sun, are quite well constrained, so we can in some sense work around them. But these atmospheric neutrinos, which come from cosmic rays hitting our atmosphere, those are the ones that are wearing really good disguises and will look a lot like dark matter signals in a liquid xenon detector. That means that as our detectors get bigger and more sensitive, they won't be able to distinguish any dark matter signals from all the neutrinos. That's what we call the neutrino fog. At the moment, we're okay, but it's going to be a problem in the future.
Okay, but can't you use some statistics to figure out if there's dark matter there as well as the neutrinos? Demystifying it with maths?
It's a nice idea, but the statistics aren't in our favor here, because we're expecting to see lots of neutrinos and relatively few dark matter interactions. Suppose you expect to spot about 5 neutrinos in a year. If you see 10 interactions in your detector, you might get excited. It's really unlikely that all 10 are neutrinos. But now imagine you're expecting to see about 1,000 neutrinos, and you detect 1,005 interactions in your detector. That's still about 1,000, so you aren't going to be able to tell if those extra 5 are dark matter particles or just a random fluctuation in the number of neutrinos. In order to definitively say that we found a dark matter signal in this case, we'd need at least 30 extra interactions. And at that point, looking at our exclusion plot, we know that dark matter won't interact very often. That's why the neutrino fog is a problem.
So does that spell the end of dark matter detectors? Can't you just put your fog lights on and keep driving?
Well, there's not much you can do to shield against neutrinos. They're just going to keep coming through, and any detector sensitive enough will pick them up. But there's still a lot of searching we can do with current detectors, and the next generation of detectors too. And we never know when a dark matter interaction might happen. Maybe next week, maybe next year, maybe in 5 years' time. If we get lucky, we might never need to worry about the neutrino fog. Plus, there are ongoing efforts researching technologies that could help us solve this problem. Even if it does spell the end for this kind of search, other dark matter candidates, like axions, are fog-free.
Maybe dark matter science's loss is neutrino science's gain. Are there interesting things you can find out about neutrinos from your detections?
Absolutely. Because dark matter experiments are optimized to search for dark matter, they're set up differently to neutrino experiments. So experiments like Lux-Zeppelin can measure energy deposits 1,000 times lower than the lowest energies neutrino experiments like DUNE can spot. It's even possible atmospheric neutrinos that hide the dark matter will show us some new neutrino physics, such as sterile neutrinos or unexpected neutrino magnetic moments.
Sounds like it's a good time to be looking for ghosts. Thanks, Kimberly.
Thanks, Kirsty. Great to spook to you.
So in the future, the neutrino fog really is going to limit the ability of WIMP detectors to search for dark matter. At that point, WIMP hunters will have to go back to the drawing board. But we're not at that level yet, and in the meantime, maybe, just maybe, they'll spot a WIMP and perhaps even shed some light on neutrinos. Would you rather spot dark matter or find some cool new neutrino physics? Let us know in the comments, and don't forget to like and subscribe, otherwise you might find you've missed the next episode of Even Bananas. Missed as in fog, as in neutrino? Oh, forget it. Fun fact, it was way back in 2007 that physicist Jocelyn Monroe first realised neutrinos were going to be a problem for dark matter searches. Back then, Monroe called it the neutrino flaw, but now scientists have a bit more hope and have started to call it the neutrino fog.